So within Chapter 2, we're going to introduce motion diagrams. We're going to look at speed and velocity and start looking at how things move, why things move. Okay? So we're going to start by looking at motion diagrams and being able to picture motion that's happening. Okay? We're going to be able to draw what's happening in our word problems by depicting that motion in a graphical way. Okay, so in the physics world, the motion that we're talking about happens all the time. Okay, it's everywhere. We pay attention to motion. We like to watch things go by out the window. We like to watch things move rather than things sit still, right? We need to start thinking about motion in terms of positional changes, in terms of time intervals, in terms of how far something's moving. That's what position changes mean. But we need to start thinking of things in terms of kind of our physics definitions now. So how far it ended up from where it started, how long it took to get there, at what rate was it moving, or what speed or velocity. Those are rates. That's what we're going to start talking about in our diagrams here. First thing we'll look at here is straight line motion, and we're going to cover most of the semester using straight line motion, things moving pretty simply from point A to point B, okay, either in a vertical or in a horizontal way, point A to point B, but straight line motion. We'll look at circular motion in terms of gravitational motion, like movement of the planets, things like that. We'll look at rotational motion. We'll look at arced motion. Which is, can anyone think of another term for something moving with an arc through the air? What do you think? Yeah? But did anyone know what the actual motion of it's called? As something flies through the air? Okay, those are called projectiles. Okay, projectiles. That's what arced motion is called. It's moving both horizontally and vertically. Projectiles are some of my favorite chapters in physics, so it's kind of fun to look at both horizontal and vertical at the same time. And then you look at back and forth motion, so vibrational type motion. We won't get much into vibrations at all. But like I said, first we're going to start with straight line motion, and we're starting with straight line horizontal motion. So things moving simply from point A to point B on the ground, on the surface of the earth, with pretty simple paths, okay? So when we talk about motion in physics, we've always got to relate it to a place and a time, or a distance and a time, or a displacement and a time. We're looking at how far it's gone in a certain time interval, okay? So if you take a look at this picture here, this vehicle's moved from point A to point B in a specific amount of time, okay? I think that may be the most vague statement possible. Okay, but that's essentially what we're talking about here, is that objects move from point A to point B. This is how far they moved. This is how long it took them. And we can do a lot of different calculations based on basically that information. Okay, so that's considered a motion diagram right there. It's just showing that this vehicle moved from point A to point B. It took a specific amount of time. Okay. So when we talk about motion diagrams, there's a lot of different ways to draw motion diagrams. We are going to just speak pretty generally about motion diagrams in that they are a way for us to describe motion of an object or movement. Motion diagrams give us a pictorial view or a mental image of what's happening in motion. Okay, so they can be series of images showing it at time intervals. They could be your little scratch drawings on your homework. They can be very, very in-depth or very general. Motion diagrams can be lots of different things. Okay, but this is what our book tells us a motion diagram is. Okay, series of images showing positions of a moving object at equal time intervals. So here's the guy running, right? Every little dot, every picture is at a specific time interval. So maybe it's every 1 second, or maybe every half second. Okay, it doesn't tell us here on our motion diagram. Those pictures or those images are taken at specific time intervals. So here he's covering in the same amount of distance every time interval because he's evenly spaced apart. So we would be saying he would be moving at constant velocity. All right, and we're going to talk more about that here in a little bit. But if he's moving in the same distance over the same amount of time every time, that means he's moving at constant velocity or constant speed. Okay, does that make sense? Okay. So when we look at graphing our motion, or when we look at starting these motion diagrams, we have to deal with a coordinate system. Okay, we deal with a coordinate system, and we use the cardinal directions. Okay, what are the cardinal directions? North, south, east, west, right? You're going to become really good at using cardinal directions to describe motion. Okay? When we draw these motion diagrams, we get to pick the origin of our coordinate system. Okay? We get to pick where our motion starts from, essentially, or where we are grounding our coordinate system or our motion diagram. We get to pick that origin. Okay? I always pick my origin where the motion starts, where the motion begins. And that'll become a lot more clear when we start actually drawing our diagrams and things like that. But it is important that you get to pick the origin. Okay? So wherever you set the origin to be on your motion diagram should be where time and position of the motion is 0. So where time is 0, where the motion is starting from, and where the position is 0, so that the object hasn't moved at all. Those should be two specific things you look for when you're picking an origin. Okay, where your motion starts from. That way your time equals 0 and your initial position equals 0. Okay, so in straight line motion, we're looking at straight line horizontal motion. That means the x-axis of our coordinate system can act here as our entire coordinate system. Okay, straight line motion. Okay, it says the straight line the motion is in becomes the horizontal axis of the coordinate system. So since it's moving very simply from point A to point B on a straight line, we're looking at just the x-axis here. Every point along that motion can be found on the x-axis. Okay, so we can indicate how far an object is moved from its origin by drawing an arrow to its final position. We can see basically how far it is from where it started just by using the ticks on the coordinate system or your motion diagram or whatever you're using to indicate that motion. Okay, so the x-axis is going to become basically our entire motion diagram in this straight line motion. Okay, there's two distinct ways that we can talk about how far something has moved. Okay, and those two terms are distance and displacement, and they're two very different things. So distance is the total amount of length, okay, and I don't want to use the word distance in its definition, but the total amount covered, where displacement is how far you ended up from where you started. So those are two very different things, and I'm going to show you kind of the difference in those two things. Okay, so distance is total amount of maybe steps that you took, total amount of meters that you covered. Displacement is how far you ended up from where you started. So we're going to look at two different types or two different ways to measure things. Okay, things can be measured as either a vector or a scalar. Okay, vector is a representation of motion that has both magnitude and direction. Magnitude and direction. Okay, so saying that I ran forward 4 meters is an example of a displacement vector. Because 4 meters, that's my magnitude. Forward is telling my direction. Okay, so some examples of vectors that we are going to use. Displacement is a vector. That means displacement must have both magnitude and direction. Displacement is a vector. Velocity is a vector. We haven't gotten to that yet. That's okay. But you can write these down as examples of vectors. Acceleration is a vector. We haven't gotten there yet. But those are things that have to be represented with both magnitude and direction. So they've got to have those north, east, south, west. They've got to have a positive or a minus. Those things indicate direction for us as well. Okay, does that make sense? Magnitude and direction are two things a vector must have. Okay, so displacement is a vector. Must always have direction, must always have magnitude. Okay, scalars, on the other hand, are quantities that only have a magnitude. They don't include direction with them. Scalars only have a magnitude, and a magnitude would just, let's say, if I say I ran 4 meters, it doesn't tell me in which direction. So this would be a scalar. Okay, but if I said I ran forward or I ran north 4 meters, that's a vector. That's an indication of a displacement because it includes direction. So some examples of scalars are distance, time, and temperature. So we see the difference between distance and displacement. Distance does not have a direction, and it's the total amount covered. Displacement must have a direction, and it's how far you ended up from where you started. Okay? All right, so let's graph some motion here. We're going to basically just see what this motion looks like. You're more than welcome to graph this as we go, but that's totally up to you. Using a coordinate system, a basic coordinate system, we can use our true origin as our origin, okay, as our starting point. So we're going to assume that this direction is always north, which means this direction right here is always what? East. Okay, this would be south, and this would be west. We always indicate north and east to be the positive directions, west and south to be negative directions. Okay, that should be pretty intuitive, right? Okay, to the right and up are always positive, to the left and down are negative. Okay, so let's start at our origin here. Our first step would be to run forward 2 meters. Okay, so can you see that blue okay? You run forward 2 meters. Run backward 6 meters, so backward would be in the opposite direction, so we'll go 1, 2, 3, 4, 5, 6 meters backward. Run forward 4 meters, 1, 2, 3, 4, we're back at our origin, and 5 meters forward is 1, 2, 3, 4, 5. Okay, so that's where we end up right there, that big blue dot. Okay, does that make sense in graphing that motion? Okay. All right, we're going to talk about the ways that we do that here in just a second. Vectors can be added graphically, which is what I just did on that coordinate system, whether you recognized it or not. What I did was add those vectors graphically. Okay, so a vector, like a displacement vector, like a velocity vector, like an acceleration vector, any indication of motion that has magnitude and direction is indicated with an arrow. Okay? So anytime you see an arrow, you know that that's a vector, so it's representing something. These vectors should be drawn to scale, okay, to the actual motion represented. So if I have a vector here that I've labeled as 6 meters, and I have a vector here that I have labeled 10 meters, that doesn't work. Okay, they've got to be drawn proportional to each other. Okay, so if I see a longer vector arrow, that means that's a longer displacement or a faster velocity or whatever. Okay, they've got to be drawn to scale here. Okay? We added them in what we call the tail to tip method. So as you draw a vector, this is the tip, this is the tail. I guess I shouldn't probably draw those with arrows. Okay, tip, tail. when you draw these vectors one on top of the other, you've got to add them with what we call the tail to tip method. So you begin with the tail at the starting point of the motion. So as we looked at our coordinate system, our first arrow went in the direction of the motion and it started at the origin. After that, you add them on top of each other. So from the tip of one arrow goes the tail of another, and you add it on top. From that tip goes the tail of another, and you add it on top. And I'm going to show you again when we graph that same motion so you can see it a little bit clearly. Okay. Tip of the arrow always goes in the direction of the motion. So if you have a vector that's saying 10 meters west, does that vector correspond with that? No, not if it's going east. Okay, you've got to make that tip go in the direction of the motion. Okay? Questions on tail to tip method? It's going to become a lot more clear when we start looking at drawing the graphs, but I wanted to introduce it to you first. Okay? When we add things tail to tip, when we add these vectors tail to tip, we have what we call a resultant vector. Okay, a resultant vector is the sum of all those vectors that you drew. Bless you. Okay, so the sum of all things that you drew is called the resultant vector. Okay, and I'm going to draw these things out and I'm going to show you what our resultant vector looks like here. Okay, so the resultant vector, I want to write this in because I want you guys to write this in. Resultant vector always goes from the origin to the tip of the last vector. Okay, so your resultant vector always starts from your origin and goes to the tip of your last vector. Because what the resultant vector is telling us is basically how far you ended up from where you started. That's our resultant vector. Okay. So let's look at that same runner example that we looked at here just a second ago. I'm gonna regraph that so you can see the tail to tip method in action kind of here. Okay, and we'll look at our resultant vector. We'll see if you can label that resultant vector. Okay. So here are origins in the middle. My first is to go 2 meters forward, okay, or in the positive direction. So here's my first vector. The tail starts at the origin, and it goes in the direction of the motion. Are we clear? Okay, our next vector needs to go from the tip of the last vector in the direction that we want. So we're going to go backward 6 meters. So we're starting at the tip right here, and we're going to go 1, 2, 3, 4, 5, 6 meters backward. Okay, so we went from the tip in the direction of our next motion. Does that make sense? Do we see it? Okay. Next one, we go forward 4 meters, 1, 2, 3, 4. We happen to be back to our origin. That's coincidental. That doesn't mean it won't always happen like that. Okay, and our last vector, we're going to go forward 5 meters. So 1, 2, 3, 4, 5. That's where we end up, right here. Okay, so now if I want to draw a resultant vector, which I'm drawing in this blue color, where does my resultant vector go? From the origin to the tip of the last vector. Okay, it just so happens that those vectors look the same. Okay, that's totally coincidental. That's not how it always works. Okay, does that make sense? Okay. Questions on that example? So this blue vector right here was our resultant vector. We started at our origin. We went to the tip of our last vector. Okay, so tell me what our resultant vector, tell me what our displacement here, our final displacement is for this person. 5 meters east or forward. Okay, very good. Remember, displacement must have a direction with it. Very good. Okay, so let's look at this vector here. We want to go 11 kilometers north. then 11 kilometers east. So we're going to say that each of these tick marks are 2 kilometers. That might not even work. Let's say that they are 3 kilometers. Okay. So our first vector, we started our origin here. We want to go 11 kilometers north. So 11 kilometers is probably about right here. So I went 11 kilometers north. Now I want to go 11 kilometers east. So do I start my next vector from here or from here? From the tip of the last one. Okay, so we want to add these vectors graphically. So we start from the tip of the last one and we want to go 11 kilometers. So 3, 6, 9, 12. To about right there. Okay, those two should be drawn exactly the same length, right? Because they have the same magnitude. Okay, good. Now tell me where our resultant vector should go. We want to go from our origin to where? Good. Okay, so if this side is 11 kilometers, and this side is 11 kilometers, does that mean that the resultant vector is 22 kilometers away? No. How do we solve for the resultant displacement?
A squared plus B squared.
Okay, so do that. Solve that Pythagorean theorem for me and find our resultant vector. Will our resultant vector be larger or smaller than 11 kilometers? Larger. Should be larger, right? Because it's the hypotenuse of our triangle. So tell me what we got for our resultant vector magnitude. 15.5 kilometers. But in what direction?
Northeast.
Northeast. Exactly northeast, or couldn't we find this angle right here? Can we find that angle? Yeah, we can. Right? We have the opposite side, we have the adjacent side, and we're going to solve for an angle. Okay? So we're going to dive in and do this right now. Okay? This is not what we're doing in chapter 2, but I want you to see that you can do it. Okay? So we're going to go ahead and solve for this angle right here just for fun. Because it's so fun. Okay, so if I want to solve this angle right here, if I'm solving for an angle, what do I have to do on my calculator? When I solve for the angle, I have to hit second tangent, right? I'm using the opposite side and the adjacent side. So make sure, first of all, that your calculator's in degrees. This class should always have calculator in degrees, not radians. If you're in pre-calc, your calculator might be in radians, so we want to switch that when you come in here. If you go to mode, we're going back to straight line motion here, so only X motion, not X and Y. Okay, only X motion here. So this is our time interval here. What's delta mean? Delta means, yeah, close. Delta means change in. Okay, delta in itself means change in, or final minus initial. So our time interval here is final time minus initial time, okay, or delta t. So here's our little runner guy again. If we are wanting to look at the time interval between 5 seconds and 25 seconds, that means we're looking at a delta t of 20 seconds, right? Our final time was at 25 seconds. Our initial time was at 5 seconds, okay, if that's what this is saying here. Okay, very rarely in our problems will we have a starting time and a final time. Most of the time we'll just say it took 5 seconds, right? That's our delta t in itself, okay? But that's what the interval means, final minus initial. So whenever you see delta, it should be final minus initial. All right, and here's our displacement that we talked about, displacement vectors. Final and initial locations. Our displacement is how far you ended up from where you started. Okay, your book labels displacement as a lowercase d. So lowercase d will always mean your displacement, your position, your location. Okay, displacement should always be labeled with that lowercase d. What do you think the units for displacement would probably be? Yeah, meters. Okay, meters. So we need to be good at picking out variables based on their units from our problems. Okay, so if we're given a problem that says they traveled 30 meters in 10 seconds, that means we've got a displacement and we've got a time. Okay, we've got to be able to pick those variables out based on their units. Does that make sense? Okay, so let's make sure that we're able to pick that out. For our time interval, what should our units be? Seconds. Yeah. Could be hours, could be minutes, but most of the time we want it in seconds. Okay? All right, so displacement's how far you ended up from where you started. It's a vector quantity, which means it must have magnitude and direction, and we talked about that briefly already. Okay, it's represented by an arrow, like all vectors are. Okay? It is very, very, very important that you understand vectors must have those two things. Okay, that might be a test question that comes up often. Vectors must have what two things? Magnitude and direction. Displacement is a type of vector. Okay, there's lots of different vectors. We're going to talk about displacement vectors first, then velocity vectors and acceleration vectors. Force vectors, we're going to get to all that stuff. But vectors in themselves have to have a magnitude and they have to have a direction.